Hello, and welcome back. We are on day 7. Let's get into it. So for this one, we get this kind of rectangular input, looks like grid. And the deal is that we have a beam that is shot down from this point marked with S. And then along the way, it'll hit these caret symbols. And the caret symbols are splitters. And so when it hits a splitter, the beam continues one to the left and one to the right. And basically it keeps on going down until it reaches the very bottom and just kind of like falls off the board there. And for part 1, the question is how many times will the beam be split? Or I guess a different way to phrase this question would be uh, how many splitters does the beam hit? Like there's this one here you can see in the test input that doesn't have any beams firing into it. So we wouldn't count that one, but we would count, I think, all the other splitters because they all have beams going into them. For part 2, part 2 is a little trickier. Something about a quantum tachyon manifold. And this is saying, I mean, basically this is saying like, okay, if you fire a beam down from S, how many paths from S down to the bottom are there? If you, with all the splitting and everything going on. So there are multiple different sort of paths that the beam can take in order to reach the bottom. Okay. Right, so let's go ahead and talk about how we solve this. So, I mean, the easiest way, I think, and I'll show you what I did for this in APL anyway, is we can kind of just like keep a count of the beams, and we can do like a scan or a reduction from the first row down to the last row. And so we start with one beam at this index, and then when you encounter a splitter, you add 1 to the beam count on either side of it, and zero out the beam count for the splitter itself, because like a beam shot down hits a splitter, it doesn't continue going straight down behind it, if that makes sense. So yeah, do like a couple, like a shift left, shift right, build up a scan. That's the code that I had for. I posted this on Reddit, and this essentially does what I just described. Now, I don't like this code that much for a couple reasons. I think it's fair to say that like scans and like custom scans and reductions in APL are, I can charitably say, not ergonomic. So for scans, especially if you're doing a custom scan, the behavior, like you would think you're just, I'm just like accumulating a result and it's basically like a reduction, but a scan in APL is has quadratic complexity, so O(n) squared. Why is that? Without getting into it too much, I would say like historical reasons, right? Um, and then, okay, so I almost never do like a custom scan for that reason, but you can mimic that by doing a reduction with like an accumulator that you're passing along. But even that is like, reductions in APL are like right to left. You have to have an accumulator of the proper shape in the last part. And it's just kind of like, it's just not that nice to work with. But this is that scan solution in APL. Guess what though? I'm not going to talk about this solution that much. The code is there and it's up on Reddit somewhere if you want to take a look. Instead, welcome to the latest episode of URNAB shoehorns in graph theory and linear algebra into AOC problems. So instead of doing a scan, let's think about this. So we could like treat this input as a graph instead. And like, there would be a connection like between the start and the first splitter. And then for every splitter would have a maximum of 2 connections down. Either the beam hits another splitter, in which case we would have a connection in our graph. Oh, I guess I should say that like we'll model all the splitters as nodes in the graph. So every node has 2 connections. Those connections will either be to another splitter or to the very bottom of the board, right? And then the question is, okay, for part 1, it's how many nodes have a valid path, any valid path from the top, our first splitter. And part 2 is how many total paths can be taken in order to reach the bottom of the board. So you can kind of think of it like a graph problem in that way. Yes, this is overkill for this problem, and you can get much terser solutions by doing the sort of like scan shift thing that I was saying. But this is I like constructing these graphs and doing like kind of linear algebra-ish solutions to them. So we're going to roll with it. All right, let's start with our test input. So inget test7.txt. We can mix it. We get our input. And we are solely going to care about these splitters. By the way, like I was looking at this, and this is like if all the splitters were there, the solution here would basically be an enumeration of like Pascal's triangle. But it gets tricky because some splitters are missing. And that means that like the count for a particular node might have like a dependency on any like arbitrary previous node. I was like messing around with like Pascal matrices and like, I don't know, Catalan numbers and stuff, but I didn't find like a closed form solution for this. If anyone took a look at that, I would be curious to see if there's a way to model the problem that way. But anyway, that's neither here nor there. Back to graphs. So we only care about splitters because basically the start always, at least in my input, and I think looking around at other people's solutions, the start always shoots the beam down into the very first, down into the topmost splitter. So if you think of it like a lopsided Pascal's triangle, it's shooting at the top of the triangle there. And also important to note is that we have empty space padding the entire border of our input. That's true for the test input here, and it's also true for my actual problem input, which is useful. So just keep that in mind. So we have a Boolean matrix where ones denote all these splitters. Now I'm going to flip this around the horizontal axis. So we're going to work top down here, at least for a little bit. And if we're going to try and build a graph, it would be cool if each one of these had like a unique ID. So we can do like at iota jot length. So at is just that's just kind of like a replacement mechanism, or it allows you to pick certain values and then like run a function on it. So it picks all the locations where there's a 1 in this Boolean matrix, and then assigns sequentially increasing IDs to them. So now each one of our nodes, rather than just being a 1 in a Boolean matrix, has a unique ID associated with it. And I'm going to add 1 to this. So our first node here in the upper left corner starts with an ID of 2. And the reason I'm doing that is we are going to treat the bottom of well, now it's the top because we swapped it around, but I'm going to treat the bottom of our input as basically a giant node. And for part two, we're going to be counting how many possible paths there are to the bottom. And by treating the bottom as just like a giant node, it makes it easier to calculate that. So let's call this like in, I guess, for nodes. And then it would also be nice to have the coordinates of our nodes, but we want to exclude our special node, the bottom, so we can do like 1 greater than, nope, 1 less than. And then we can pull out all the indices with where, and we can assign this to like C for coordinates. So now um, we have our input transformed, flipped around. Every splitter has a unique ID associated with it, and the bottom is all marked with the very first such ID. And then C is all our coordinates for the splitters, not including the bottom. All right, so every splitter can have a maximum of 2 connections. It splits once to the left, once to the right. Those 2 connections could either be to another node, or they could be to the bottom. So if we do like a max scan first on in, this tells you, so for any given point in the column, it tells you what the most recent node would be encountered along that column. And now for any, so if we think about our original points in this input here, we can, for every node, we can grab the number to the left and the number to the right, and that will tell us the nodes that it connects to in the graph. We can do that with a rotate, something like, you have to enclose that, like so. Rotate wraps around, but remember that we have padding around our input, so we should be okay here. And then we can mix this into a rank 3 array with this shape. And if we look at the shape of our transformed input, it would be nice to be able to use our coordinates here to index into this rank 3 array and pull out like the 2 nodes that it connects to. This is not quite in the right shape for that. If we transpose it, we are almost there because now the 2 elements that we want are on the end, and we can index into the first 2. But our rows and our columns have gotten switched around. Transpose basically like reverses all of the axes. We can fix that with a transpose rank 2 before we feed it in there. And now we have an array of the right shape. So this is going to flood the terminal, but that's okay. It looks like this. So for each row and each column in our inputs, we have 2 kind of like node indices here that denote what the closest like node ID along that column would be. Okay, so we have that, and then let's go ahead and like get our if we had, so we can take length C, and that's 22, but we have to add 1 to it, and then iota. So this is just a count of all the nodes in our graph. If we look at in, you see, so the maximum node here is 23, and we just have a vector from 1 to 23. And then if we take this and we go back to the rank 3 array that we were constructing, we can put this on the left side, and we can do a let me think about this. Oh, actually, let's do this instead. So let's, for each one of our coordinates, we will index into this rank 3 array. I think I have to enclose this like so. And this gets us the, for each one of our coordinates, this gets us the node IDs for what it connects to. Now we can take our vector of all of our node IDs, sequential, and we can do a rank 1 function here. This is like, let's see, plus slash dot equals, something like this. And this will, let me think about this. Oh, let's mix this here. Yeah, okay. So a lot just went on there. So we have so we have our list of coordinates here. Because every node can at a maximum have 2 connections, we can just mix it. And then the idea is that we want to transform this into like an adjacency matrix to represent the graph. And we do that like I was saying previously. So we generate the vector of all of our node IDs. And then we take that row for each one of these rows in the matrix that we've just constructed. And this jot dot equals is an outer product, so it'll generate a Boolean matrix where ones denote these 2 numbers here. And then we can do a plus reduce to add them together. The reason we're doing it this way instead of like membership or something, by the way, is because some nodes have duplicate elements. So especially like the nodes in the bottom of our input will have like 2 connections to the very bottom of the board. And we want to make sure that like we're constructing a like a weighted graph where nodes that have 2 connections to the bottom show up properly. So let's take a look at our graph matrix here. And yeah, so remembering that we kind of like flipped our input around, this more or less looks correct. So like our first nodes would be at the bottom. They have 2 connections to the very bottom row. And then there's like a kind of string of connections continuing up. The shape of this is not quite square. We're missing a row, and that's because we had our very special bottom row as a node. And we can represent the bottom nodes in this adjacency matrix. It's just a row of zeros because the bottom doesn't have any connections outgoing from it. It's like a terminal node. Now, this is still a little bit confusing because we did some flipping around. So we can restore the proper order of things by flipping around the horizontal and vertical axes. And now the top row denotes the very first splitter that the beam encounters. And then you can see here that other nodes have 2 connections to the very bottom index. The very bottom index doesn't have connections to any other nodes. So, and this is a square matrix, so we've covered everything. Let's assign this to M. Okay, so how do we actually work with this graph? How do we actually work with this graph and get our answers? So we can think about like, imagine that we had a vector that has like all the beam counts that hit the various nodes, right? So we start with the beam of 1 at the very top, and we kind of iterate and figure out what all the beam counts should be. Then our part 1 answer would be, okay, how many nodes have at least 1 connection to the very top? And our part two answer would be how many connections from the top to the very, like the special bottom node that we constructed are there. So if we do like length C and then 1 plus because of our special nodes iota, this is again just like a vector of our sequential node IDs. We can do 1 equals so that we start with like a beam at the very top, right? And, you know, I've done a couple videos where I go over this in more depth, what I'm about to do. I'm kind of breezing through this. Maybe I'm kind of breezing through it in general. I hope you're all still with me. But I'll link I think it was like a 2023 video where I went into more depth about this particular graph transformation. I'll link it in the video description, but just to, it turns out that we can like kind of iterate through the, graph via matrix multiplication. So I think we do like, you have to do it the other way around. So if we take our vector and do a vector matrix multiplication with our graph, we get this, and this is like a single step forwards. So we started with a beam at the first node, and then it splits, and now we have beams at the second and third nodes. And we can take our original vector and add it like so. And this is kind of like keeping a running tally of the beams at every node. Let's reformulate this a little bit so that we're keeping our original one vector there. And now we can iterate with the power operator. So we can do this 2 times, and we can kind of see like, okay, the beams are splitting, and now we're getting more counts here. The counts at the beginning aren't exploding upwards because there are no loops in this graph. You know, every splitter connects to a splitter further down. There's no way for like a splitter further down to you know, connect back to a splitter further up. We can iterate it 2 times. We can iterate it 10 times. And if you've seen my videos, it should be no surprise that we can do like a power match. So we can basically run this until it converges. Yeah, hopefully that makes sense. And then our part 1 answer would be, okay, if we drop 1 because we added a special nodes and then take the sign and we add everything together, we should get our part 1 answer. Let's see. Yeah, for the test input, it's 21 times. And then if we're interested in our part 2 answer, we can just look at the path count for the very last node, which corresponds to the special like bottom node that we constructed. It should be 40. And looks like that is the case for part 2. Okay, now if we don't mind doing a little more work, I'll show you something interesting. So instead of doing this with, how should I do this? So instead of doing this on just a vector, so we start with a vector of our node IDs, and we can construct an identity matrix like so. And this identity matrix has the same shape as our graph. And you can kind of think of the identity matrix here as saying, okay, assuming that each one of these splitters has a beam firing at it, how many paths does it have to other nodes? And this actually works just fine with the same formulation that we were doing. So you can do this. And this is overkill for the problem, right? because we don't like we're doing more work than we need to here because we're basically solving the problem not just for like a beam from the very top of the triangle, but from every possible splitter. And then just, so we can take the first row here, and this vector here is equivalent to previously when we were just working with a single vector. But the cool thing about this formulation is it turns out that so we're doing sort of like repeated matrix exponentiation here, kind of, sort of. And there's a closed form solution for it. So if we go back to our identity matrix here and we subtract our graph, we can do this all in one shot by taking the inverse of this matrix, which I think is really cool. And I basically look for any opportunity to use this that I can. Once you have the inverse, you can index the first row, and we can assign this to R, and then, just like I was saying previously, take the sign, sum it, and we get our part 1 answer, and then part 2 is just the last element of R. So it's kind of a whirlwind tour of this. Like I said, I'll link the video where I go into more detail about this graph transformation and like where this interesting kind of correspondence between repeated matrix multiplication and addition and the inverse operator comes from. But if we look at this alternative solution for part 2, or for day 7, it looks like this. And so we can run it on the full input, and we see that we get 1539 and something ending in 864. Well, for part 2, that's correct. And then for part 1, that's also correct. Now, this is pretty wild because because we are constructing like an adjacency matrix for the graph, it means that the graph is quite large. So it's how many elements is this? This is almost 3 million elements in the graph. It takes almost 3 megs to represent in memory. But you know what? Matrix inverse is a very fast operation. So even though we're doing way more work here than we need to, it still runs quite quickly. So yeah. So that's I went over very briefly this kind of like scan, well, really reduction based solution. Then I went into more depth about this kind of like overkill, build a graph and do some matrix stuff to figure out the answer. But I prefer this answer. I think it's cool. Anywho, hopefully you enjoyed this, and thanks for tuning in.